Hello students, welcome to mathematics class. In this class let us start with the new unit, that is Fourier series, and it is the second unit of your syllabus. So here already we have completed two units, the differential equation 3, that is the fourth unit, and differential equation 4, that is the fifth unit. So two units of your fourth semester have been completed, and now let us start with the second unit, that is Fourier series, and unit 3 is Fourier transforms, and unit first is the group theory 3. So here now let us start with this Fourier series. So in this unit we are going to discuss periodic functions, Fourier series of functions of period 2 pi and 2l, Fourier series of odd and even functions, and also half range sine and cosine series. So these are the topics to be covered in this Fourier series unit 2. So first of all, already we know what are the periodic functions that we have came across in PUC and also in B.Sc your previous semesters. So therefore let us discuss the definition and examples of periodic functions, even functions and odd functions. So now the first definition is periodic functions. So here a function f of x is said to be periodic function if it is defined for all real x and there exists a positive integer t, capital T, such that f of x plus t is equal to f of x, where t is called as period of the function f of x. Means at the regular interval of the values of x, if the values of f of x are repeating, then thus such functions are called as periodic functions. For example, sin x, cos x. So here we know the graph of the sin x. So here this is the graph of the sin x. Now it is for x equal to 0, this is for x equal to 2 pi. So if you start again plotting the graph of sin x, again from here it will go like this, again this, means the wave from 0 to 2 pi is repeating again. So therefore such functions are called as periodic functions. So therefore here we can say that here from 0 to 2 pi one curve, that complete curve is completing, and again from 2 pi to 4 pi it is having the same wave or same curve. So therefore that 0 to 2 pi, this length or this interval is called as period of the function, because at every regular intervals of that the sine wave is repeating. So therefore this 2 pi is the period of the function sin x, and similarly for cos x. So therefore sine and cosine are the periodic functions with the period 2 pi. So therefore sin x equal to sin x plus 2 pi, and similarly sin x plus 4 pi, sin x plus 6 pi, and so on. The in general sin of x plus 2 n pi is equal to sin x only, and similarly for cosine function. So therefore these such functions are called as periodic functions. And next, even function. A function f of x is said to be even function if f of minus x equal to f of x, means if you replace x by minus x in the given function, then the original function is not going to change and it remains its originality. So such functions are called as even functions. For example, x square, x power 4, x power 6, and so on. Here x power, even power of x, they are all even functions, and then cosine and secant x are even functions, because we know that cos of minus x equal to cos x, means if you replace x by minus x, then also that cos x will not change. So therefore cosine function is the even function, and here x square, and x power 4, x power 6, all even powers of x will be considered as even functions. And then odd function, a function f of x is said to be odd function if f of minus x equal to minus f of x. So such functions are called as odd functions. So here these are the examples: x, x cube, x power 5 means all odd powers of x, and then sin x and cosec x. So here sin x, so if you consider sin x and if you replace x by sin x, then it is equal to minus sin x. So therefore f of minus x equal to minus f of x, then such functions are called as odd functions. So these are the examples of even functions, odd functions and periodic functions. So this definition is important, that is periodic functions. Next, let us discuss how to write the Fourier series for the function which is defined in the, or which is having the period 2L. So this is the Fourier series for the function of period 2L. So here period of the function can be calculated by the given interval. So here a comma a plus 2L is the given interval. If you consider the length of that interval, so length means upper limit minus lower limit, so that will give the length of the interval. So here length of the interval can be considered as the period of the function if the function is periodic. So here let f of x be defined in the interval a comma a plus 2L and f of x be periodic. So here if f of x is periodic, then only the length of interval is called as period of the function. Otherwise we cannot say that the length of the interval as the period of the function. So here f of x is periodic with the period 2L. So here we can obtain that 2L by subtracting upper limit by the lower limit. So then the function f of x can be expressed in the form of the following series, where L is any real number. So therefore here L may be any real number. So if the function is having the period 2L, then the Fourier series can be written as f of x equal to a naught by 2 plus summation over n equal to 1 to infinity a n cos n pi x divided by L plus summation over n equal to 1 to infinity b n sin n pi x divided by L, where a naught is equal to, so here a naught, a n and b n, they are all constants, and those constants are given by the following formulae. So these three formulae are called as Euler's formulae, and this a naught, a n, b n, they are called as Fourier constants or Fourier coefficients, a naught, a n and b n. So now a naught is equal to 1 by L integration over a to a plus 2L, that is lower limit of the given interval where the function is defined, and a plus 2L f of x dx, and a n is equal to 1 by L a to a plus 2L f of x into cos n pi x divided by L into dx, and b n equal to 1 by L a to a plus 2L f of x into sin n pi x divided by L dx. So here if you remember this f of x correctly, no need to remember these three because they are easy to write. So a naught by 2, so a naught equal to 1 by L a to a plus 2L f of x dx. Then while writing a n, you have to repeat the same, that 1 by L a to a plus 2L f of x, and a n is multiplied by cos, the same term you have to consider here. So therefore that is a n, and b n equal to again 1 by L a to a plus 2L f of x. Now b n is multiplied by this sine function, the same function you have to consider here. So these are the Fourier constants, and these three formulae are Euler's formulae to find the Fourier constants. So therefore this is the Fourier series when the period is 2L, means if the function is defined in the interval a to a plus 2L. then only we are going to using the series f of x equal to a naught by 2 plus summation over n equal to 1 to infinity a n cos n pi x divided by L. What is L? Period is 2L and we have to consider half of that, and n equal to 1 to infinity bn sin n pi x divided by L. So this is the Fourier series of the function of period 2L. Next let us discuss the Fourier series in the interval or in the with the period 2 pi. So if the function is having the period 2 pi, then how to write the Fourier series? So if f of x is a periodic function with the period 2 pi, then we have f of x is equal to a naught by 2 summation over n equal to 1 to infinity a n cos nx plus summation over n equal to 1 to infinity bn sin nx. In the interval it may be minus pi to pi or 0 to 2 pi, because both the intervals are having the same period. Period means that is the length of the interval. So here upper limit minus lower limit, that is also 2 pi, and here upper limit 2 pi minus 0, that is also 2 pi, means these two intervals are giving the same period 2 pi. So therefore here we can take two intervals minus pi to pi and 0 to 2 pi which are having the same period. So therefore here a naught is equal to 1 by pi minus pi to plus pi f of x dx, and a n equal to 1 by pi minus pi to pi f of x, here cos nx, and bn equal to 1 by pi minus pi to pi f of x sin nx dx. So these three are the Fourier constants in the interval minus pi to pi. So if the interval is minus pi to pi, then these are the formulae for the Fourier constants, because here interval of integration is different, minus pi to pi is there, and if the interval is 0 to pi, then the formula will be like this, that a naught equal to 1 by pi 0 to 2 pi f of x dx, and a n equal to 1 by pi, sorry, here this is 0 to 2 pi f of x cos nx dx, and bn is also 1 by pi 0 to 2 pi f of x sin nx dx. There is no there is no maximum difference in these two formulae, only the interval of integration is different. Here the interval of integration is minus pi to pi, and here 0 to 2 pi, only that much is the difference in these two set of formulae. So here these are the Euler's formulae for the interval minus pi to pi and for the interval 0 to 2 pi. So here in the previous interval, that is for 2L, here a naught by 2 summation over n equal to 1 to infinity a n into cos n pi x divided by L was there. So here this is cos nx and sin nx, only that is the change in of the Fourier series for the period 2L and 2 pi. And here we have already have discussed that period of the function 2 pi. In that interval we have written the Fourier series, and if the period is minus L to L, because minus L to L is also having the period 2L only, as similar to minus pi to pi. In the previous one we have discussed that Fourier series for the function of period 2 pi. In that we have considered two intervals, minus pi to pi and 0 to 2 pi, and for 2L we have not considered minus L to L. So therefore here we are giving that in the interval minus L to L how to write the Fourier series. The formula will not change, that will be same, a naught by 2 summation over n equal to 1 to infinity a n cos n pi x by L, and plus summation over n equal to 1 to infinity bn sin n pi x divided by L. That will be same, only we are going to change the interval of integration. So here a naught equal to 1 by L minus L to L f of x dx, but there it was 0 a to a plus 2L, right? And a n equal to 1 by L minus L to L f of x cos n pi x divided by L dx, Bn equal to 1 by L minus L to L f of x sin n pi x divided by L dx. So therefore these four are the main series in the period 2L, and if the interval is a to a plus L, sorry, a plus 2L minus L to L, 0 to 2 pi and minus pi to pi. So these are in particular. So if randomly the interval was given, suppose from expand the function f of x in the interval a to b, where a and b are any two real numbers, then how to write the Fourier series? Because we know only the Fourier series having the period 2L means the function must be defined in the interval a to a plus 2L or minus L to L, or 0 to 2 pi or minus pi to pi. If randomly it is given, suppose the function is defined in the interval 1 to 2, then how to write the Fourier series for that function? So therefore here this is the formula, in the interval a to b. So this formula is in general, which is applicable for each and every interval, whatever may be the interval. It may be a to a plus 2L or 0 to 2L or minus L to plus L, 0 to pi, minus pi to pi, or 0 to 2 pi, whatever may be the interval. This formula is applicable for each and every interval. So therefore better to remember this formula only, because if you remember this formula and just by substituting the values of a and b, we can write Fourier series for every interval. So therefore this is the general formula or generalization Fourier series. So f of x equal to a naught by 2 plus summation over n equal to 1 to infinity cos a n into cos 2 pi n x divided by b minus a, plus summation over n equal to 1 to infinity bn sin 2 pi nx divided by b minus a. This is the general Fourier series, where a naught is equal to 2 divided by b minus a integration over a to b f of x dx, and a n is equal to 2 divided by b minus a integration over a to b f of x. F of x must be multiplied by the coefficient of a n in the formula, that is cos 2 pi nx divided by b minus a, and then b n equal to 2 divided by b minus a integration over a to b f of x. In place of cos we need to write sin, that sin into 2 pi nx divided by b minus a dx. So here remember this formula carefully, because whatever may be the interval given, in that interval we can expand the function. So therefore if you forgot all those four formula, it will be okay if you remember this one. So therefore just remember this formula and these three, which are the formulae for Fourier constants or Euler's formulae. And next here, expansion of even and odd functions. So if the function is neither even nor odd, then we can expand that by using the general formula, that is for the interval a b, right? But if the function is even or odd, means which are following the nature of even and odd functions, then we have some particular cases. So therefore let us expand the function if it is even and if it is odd. Only we are going to, there is a change in finding the values of a naught, a n and b n. So if the function is even and if the function is odd, there are some changes in the values of a naught, a n and b n. So therefore let us start the expansion of even and odd functions. So here by the property of definite integrals, minus a to a f of x dx is equal to 2 times 0 to a f of x dx if the function is even, and it is equal to 0 if the function is odd. So therefore here this is the properties of definite integral that you already came across in the second PUC definite integrals. So therefore if the interval of integration is minus a to a, then only its value is 2 times 0 to a, and only when function is even, and the integral is having the value equal to 0 if the function is odd. And also we know that any function defined in the interval minus L to L can be expressed as, so already we know the formula for the Fourier series in the interval minus L to L. So therefore f of x equal to a naught by 2 plus summation over n equal to 1 to infinity a n cos n pi x by L plus summation over n equal to 1 to infinity b n sin n pi x by L, where a naught equal to 1 by L minus L to L f of x dx, and a n equal to 1 by L minus L to L f of x cos n pi x dx, b n equal to 1 by L minus L to L f of x into sin n pi x by L dx. So this is the Fourier series for the function which is defined in the interval minus L to L. Now here we have two type of functions, one is even function and one is odd functions. So therefore here we are having two cases. So let us start with the case 1. Case 1, when f of x is even function. So if the function is even, then how to expand the Fourier series? So here we know that cos n pi x divided by L is even, right? Because cos of minus x equal to cos x, that is nothing but even function. So cos of any value, whatever may be the theta value, that cosine function is even function. So therefore cos of n pi x by L is even function. So therefore let us write the formulae for, or Euler's formulae, they are the Fourier constants. So therefore a naught, so a naught here 1 by L minus L to L f of x dx. So already we know that the function is even function, and this minus L to L can be written as 2 times 0 to L by using this property. So therefore here this is 1 by L, and this is equal to what? 2 times 0 to L f of x dx, which can be written as 2 by L 0 to L f of x dx, that is a naught. Means the formula is changed, minus L to L changed to 2 times 0 to L, that is the only change in the value of a naught. And then a n, so here a n is given by 1 by L minus L to L f of x into cos n pi x divided by L dx, that is the formula here, a n. The same formula we have considered here, that a n equal to 1 by L minus L to L f of x cos n pi x by L dx. So here it is given that f of x is even, and also cos n pi x by L is even. So therefore if two functions are even functions, then after multiplying, the product of those two functions is again an even function. So therefore it implies that here f of x into cos n pi x divided by L is even function, because both are even. So the product of two even functions is again even. So hence that f of x cos n pi x by L is even. So if the function is even, then minus L to L can be written as 2 times 0 to L. So therefore a n equal to 2 by L 0 to L f of x cos n pi x by L dx, that is an. And next Bn. So Bn equal to 1 by L minus L to L f of x sin n pi x by L into dx. So here f of x is even, it is given, and we know that sin theta is odd function. So therefore sin n pi x L is odd. So if one function is even and one is odd, then the product of them, it will be an odd function. So therefore that f of x sin n pi x by L dx is odd. So now Bn is equal to, what will be the value of Bn? That is equal to 0, because here minus a to a f of x dx is 0 if the function is odd. So here this total function is odd function now, and the interval is from minus L to L. So therefore its value is equal to 0. Then what about the expansion when f of x is even? So f of x is equal to a naught by 2 plus summation over n equal to 1 to infinity a n cos n pi x divided by L. Only this is the expansion if the function is even, right? Because Bn equal to 0 for the even functions. Hence this is the only expansion. There is no third term. But if the function is neither even nor odd, we can write a naught by 2 summation over n equal to infinity a n cos n pi x by L plus summation over n equal to 1 to infinity Bn sin n pi x by L. So therefore, but here the function is even, hence the value of the third Fourier constant is 0. Hence in expansion it is having only two terms, a naught by 2 and summation over n equal to 1 to infinity a n cos n pi x by L. Now let us start with the second case. If f of x is odd function, so here we know that the product of even and odd function is even, and product of even and even function is even. So here f of x is odd and cosine is even. So if you multiply by one even and one odd, then the product will be odd, right? So therefore here a naught, the first Fourier constant, that is equal to 1 by L minus L to L f of x dx. So here given that f of x is odd, then minus L to L f of x dx will be equal to 0. So therefore here a n equal to 0 when the function is odd. And the second Fourier constant a n, that is 1 by L minus L to L f of x cos n pi x divided by L into dx. So here it is given f of x is odd, and we know that this cos function is even. So one is odd and one is even, then the product will be odd only. So then this total function will be an odd function. If the function is odd in the interval minus L to L, then its integral value is equal to 0. So therefore a n is also 0. Now let us discuss about Bn. So Bn equal to 1 by L minus L to L f of x into sin n pi x divided by L dx. So here f of x is odd function and sine function is also odd. So therefore by multiplying these two, odd and odd, we will get the even function. So means now f of x into sin n pi x by L is an even function, and if the function is even, then minus a to a can be written as 2 times 0 to a. So therefore that Bm becomes 2 by L 0 to L f of x sin n pi x divided by L dx. So therefore this is the value of Bn for the Fourier series if the function is odd. So therefore now the function expansion of the function is given by summation over n equal to 1 to infinity Bn sin n pi x divided by L. Only this is the expansion of the Fourier series if the function is odd function. So here it is clear that if the function is even, then Bn equal to 0. If the function is odd, a0 and an equal to 0. The first two Fourier coefficients will be equal to 0 for the odd function, and third coefficient is equal to 0 for the even function. And in the expansion of even function, the expansion contains two terms, and in the expansion of odd functions it contains only one term, because both a0 and an are equal to 0. So now this is the introduction about periodic function and also the expansion of the Fourier series of the functions of period 2l, 2 pi, and also the interval, and if the function is defined in the interval ab, then how to write the expansion of the series. So therefore remember the formula of the Fourier series in the interval ab. If you remember that one, it is helpful for all the intervals.